All right. So, how's it going? How's the lab?
Good.
All right, I need everybody to vote. Raise your hand if you got part 1 done, phase 1.
Mostly.
How many of y'all have gotten the command interpreter stuff for phase 2 working? You have the UI phase 2 stuff working? Can you type in commands and have it actually create a process? Can you print out the process when it's done? All right. Y'all are hopelessly not going to get finished, so I'm going to extend the lab till Thursday. Okay? Don't say I don't ever do anything nice for you. The reason why I'm doing this is because the first step of Lab 9 is to finish Lab 8. You can't do Lab 9 without Lab 8 working. So you're going to be spending from Tuesday to Thursday doing Lab 8 anyway. If I make it do, it's just you're going to end up with more credit for it if I make it do later. So, not only that, but what will happen, I'm sure you guys aren't like this, but usually what happens is the moment that Lab 8 is due, you all will submit whatever you've got, working or not, and then you'll take a week off. I don't know why you have to think like you've got stuff in other classes or something. But anyway, this is also a cruel and unusual way of punishing you to make sure you pay attention to 5780 for longer. Actually, the real intent of this, joking aside, is I want you to be able to get Lab 9 done. And so you have to have Lab 8 working in order to do Lab 9. And the earlier you get Lab 8 done, the better your lives will be. So I hope that giving you the extension till Thursday at midnight will give you enough time to be able to mop up everything and get the Lab 8 essentials working so that you can then proceed on to do Lab 9. Lab 9 will be due at the end of the semester. I'll post it. I'll probably post it today. I don't know, I'll post it tomorrow. I'll post it tomorrow so those of you who are overachievers and get done and want to start taking a look at it, by all means you can have at it. But anyway, we have some flexibility with lecture time, so if you guys have questions about the lab that you want me to address in class, I'm fine with that. So, anybody have any questions they want to ask?
You say final or?
I can guarantee that Lab 9 will be due no earlier than the 4th of December. The final exam is the 11th of December, I believe that's when it's scheduled. So, usually what I've done is I've let Lab 9 be due in the middle of finals week if the final lands at the end of finals week. But I won't have it due the same day as the final because you'll just do your lab and you won't study for the final. Psychology games we have to play with you poor students. Anyway, so I will. I can't see myself making it due any later than the Wednesday of finals week. But do you want me to do that to you? Do you want me to make you have a lab due in the middle of finals week? Because here's the deal. If I make it due in the middle of finals week, that means you'll work on it in finals week. If I make it due before finals week, you'll get it done before finals week. Because you guys operate on the earliest deadline first scheduling algorithm, not rate monotonic. We're going to be talking about EDF, and EDF is used in embedded systems, but the student scheduling algorithm is EDF. And if I make the deadline later, that means you'll work on it later, which is just, unfortunately, I don't blame y'all for that. That's how I operated when I was a student. That's just how it works. So, be thinking of when you want me to make that due. So if you want to work on a lab during finals week, I'm good with that. All right. Questions about the lab? No one dares venture a comment on that one. All right. So, questions about the lab? Anybody have any questions they want to address? If not, we can barrel on into Lab 9 stuff. One of the lectures going to finish? Depends how many questions you ask. So I've got this set of slides that goes over RS-232, and then I've got another set of slides that talks about Lab 9, and that will take maybe a class period, maybe two, depending on how fast things go. And then I've got another set of slides that talks about EDF and deadline monotonic scheduling. And that's all the notes that I've got. So, we are ahead in lecture. So we've got, we will, so how I see it going right now is we'll have enough material to carry us through this week, especially because most of Friday is going to be course evaluation. We can debate about whether or not we want to cancel class Monday, Thanksgiving week. And then we have 1 week left. And so the last week of class, I will have at least one period of reviewing for the final exam. And what I've done in the past is just not lectured new material during that week and just been here for answering Q&A on the lab or whatever. See, nobody's commenting over there. 14 minutes. Problem is, every time it does this update stuff, it takes 20 minutes for the thing to reboot. So anyway, that's kind of the direction that we've got. We've got enough material to go with. You know, you're not wasting your tuition dollars. I will keep talking. I can keep talking the rest of the semester. Don't worry about that. Mitch.
On the lab, it says we have to input as a floating point number the seconds for the period of the process. So, to what resolution does that need to be accurate? Just to the resolution of our pit? Or?
So the question is, we have to put in compute time and event period as a floating point number. How accurate does that floating point number have to be? You should have yours in units of seconds. And then if you convert your units of seconds into units of pit period ticks, and it doesn't divide evenly, you just round to the nearest unit of pit period ticks. Because your processor can't tell time in a resolution that's finer than your pit period. So if the user requests some time that isn't exactly doable, then you just go to the next closest pit period.
Okay. So why is it input, if it's in second resolution, why is it a floating point number?
Is your pit period a second?
Well, I mean, what the user types in, you said just needs to be second resolution.
It should, no, I did not say it was seconds resolution. I said it was in units of seconds. There's a difference between units of seconds and in resolution of seconds. Yeah, so he could put in, the user can put in a fractional second. Good question. Another question. Y'all excited about Lab 9? Lab what? What lab are we on again? Okay. So onward and upward. Remember last time we were talking about RS-232, the 8N1, where we have one start bit, 8 data bits, one stop bit. We talked about in time transmitting data over an RS-232 line looks like this, where you have two logic levels, logic 0 and logic 1, and the line floats at logic level 1 until you decide it's time to transmit something, and then you assert a logic level 0, that's your start bit. You hold the line at the start bit logic level for 1 bit period. How long is this bit period is dictated by a predefined agreement between the transmitter and the receiver. So you configure the transmitter to transmit at a particular baud rate. You configure the receiver to receive at a particular baud rate. Both of them are programmed separately to run at that baud rate, but both of them have to be running at that baud rate. Okay? So you hold the start bit, the transmitter holds the start bit on the line for a 1 bit period, and then you individually transmit each data bit, D0, D1, and so forth, up until, and each one of those bits that you're transmitting, you hold on the line for 1 bit period. Okay? Why do you hold it on the line for a bit period? Why don't you just put it on the line and then change it immediately? Well, the transmitter's got to give time for the receiver to detect and discern what is the bit that you're transmitting. Not only that, but the longer time that you hold it on the line gives the receiver more ability to oversample the value that's on that line in case your line is affected by noise. So if you've got some spiky something or other that transient impacts what the logic level that you're asserting on a particular line, and that transient happens on a very short duration with respect to what your bit period is, then if you oversample on the receiver side, you can figure out that my 1 really is a 1, or my 0 really is a 0. So you hold the start bit, then you assert the data 0, then data 1, then data 2, up to data 7, and as soon as data 7 is done, you hold the line at logic level 1 for your stop bit. If you want to transmit again, you immediately assert another start bit, you hold that for a bit period, then you send 8 more data bits, then a stop bit, and so forth. Okay, your bit period, that's the difference between two slots on this horizontal axis here. So the difference between T1 and T0, that delta T, that's your bit period, or 1 over the baud rate. Okay, when I say bit period, when you're talking about serial transmission, you often talk about your bit rate and your baud rate. And there's a difference between your bit rate and your baud rate. Your bit rate corresponds to what's the average amount of time that it takes for me to send my package of data that I'm trying to send from the sender to the receiver. If I convert how much data I'm trying to send into units of bits, how much time does it take me to send this package of data over there? And if I take number of bits divided by total time in units of seconds, that gives me the average bit rate that I'm able to transmit data. It's only considering the data bits. When we're talking about baud rate, this is saying how much time per actual transmitted bit on the line. So if you remember, I've got to send a start bit and a stop bit in order to send 8 data bits. When you're calculating your bit rate, you say how much time does it take to transmit 8 data bits? Well, with 8 and 1, what it takes is 10 bit periods for 8 data bits. Okay, so your bit rate is going to be less than your baud rate because your bit rate doesn't consider the overhead bits for doing your framing as valid bits that you're sending. They're overhead, so they decrease the total rate. Your baud rate is more at the level of your protocol where you're just asserting information on the line. The baud rate doesn't care if it's a stop bit or a data bit. Okay, so the actual time that a signal is resident on the line, that corresponds to your baud rate. Okay. RS-232 is an inverting protocol electrically. So we have 2 logic levels, logic level 0 and logic level 1. Logic level 0 ends up being cast to this voltage range somewhere between +3 and +15. Logic level 1 ends up being -3 to -15. That's a pretty big range of voltage, and they did that on purpose so a lot of different electrical specs will work. And the level shifter chip you guys are going to be using ends up giving a voltage level at about + and -7 for the 2 logic levels. But if you use +15 and -15, that works just fine. Okay. Part of the reason why the logic levels were defined as they are is to increase the separation between your logic level 0 and your logic level 1, again to provide you some immunity to the impact of noise on your transmission. Okay. On our board, we have had experience with digital I/O. You remember the voltage levels for digital I/O are 0 volts for logic 0. Logic 1 is +3.3 volts. So what we're going to be doing is using our digital I/O module on our board to be able to transmit via RS-232 protocol to a PC that has embedded in it an actual RS-232 UART. Okay? So we've got the ability to send and receive with our pins on our digital I/O port on our board that transmit and receive that operate at 0 and 3.3. What we need to do is convert the 0 and 3.3 logic levels on our digital I/O port to RS-232 levels, which is what we showed before for a +3, somewhere between +3 and +15, and somewhere between -3 and -15. So we have to convert between these two logic levels. We use what we call an RS-232 level shifter chip. And that chip is responsible for converting just exactly what we're doing. Logic signals between that have a logic 0 of 0 volts and a logic 1 of 3.3, it inverts and amplifies so that the 0 ends up being minus or plus 7 and the 3.3 ends up being minus 7. Okay? So this is a level shifter chip. You're going to have to buy this sucker from Heidi. It comes with 4 capacitors. This particular chip is pretty slick because you don't need to supply a separate power supply for the chip. It scavenges all the power that it needs from the board. Okay, so you have to have a chip and then 4, I think they're 0.1 microfarad capacitors. It's going to cost you about $5. I will post the data sheet along with the lab. It will show you how to wire the thing up. It does the inversion, the amplification. You don't need a separate power supply. You just use the digital I/O ground and the 3.3 as the ground on the VCC. There's a ground pin and a VCC pin on the digital I/O port. That's what you're going to use for your power supply for the level shifter chip. You can separately configure the DC power supply to 3.3 if you want to. That's fine, but no need to. You can just use the board. The other thing you need to remember to do when you're using this level shifter chip, the level shifter chip provides multiple level shifter circuits inside it. So as if you were running multiple RS-232 channels. Okay, so all the other transmitter pins that you're not using, tie them to ground or tie them to VCC. If they just float, they'll provide noise and corrupt your inputs that you are using. So anything that you're not using, make sure to tie them off. All the transmitter lines, tie them off appropriately. Okay. So in software, if we're implementing a half duplex RS-232, or what we're doing, we got a PC with a wire that connects us up to our TS-7200 board, and we're sending data from the PC to the TS-7200. With the TS-7200 as the receiver, you're going to hook the wire to the input digital I/O pin. If you remember back in Lab 3 and Lab 4, we had 2 pins we were operating on the DIO port. We used one of them as an input pin, another one as an output pin. Okay? So in this example, what we're going to do is we're going to connect this wire up to the TS-7200's input pin. And then we're going to hook the wire on the other side to the PC side transmit pin. Okay? You know right now that you have an RS-232 cable that plugs into the back of the PC upstairs and then hooks into the RS-232 port of the TS-7200. Okay? In order to do this, theoretically what you would have is some other PC that's not plugged into the TS-7200 already, or you disconnect your debugging printf console I/O RS-232 and use that as a way of talking to your TS-7200. But the PC has a COM1. That COM1 has the capability of doing full duplex communication. It has a ground pin, and it has a transmit pin, and it has a receive pin. In order to figure out which one's transmit and which one's receive, you got to probe the pins of the DB9 connector for your RS-232. So you got to figure out which one is. So you use your scope and you figure out which one's driven to logic high. So what that'll do is one of those pins coming out from the DB9 connector will end up being driven at minus 10. That's the PC sending a stop bit. Okay. Whenever that COM port is on, it's always sending a stop bit. You got to figure out which pin is sending the stop bit. Okay. So you can find the one that's being driven to minus 10. That's your transmit pin. So you would then connect up that pin on the DB9 connector coming out of the PC and connect that up to your input pin on your DIO header. Okay. So now, how do we go about doing a receive on the TS-7200? Okay. In order to do a receive on the TS-7200 in software, we have to kind of watch what that pin's value is, the input DIO pin. So there are 2 strategies. You can either use the DIO interrupt or the DIO interrupt in a timer, or you can use the timer interrupt. Okay. If you use the timer interrupt, this is kind of like an A to D. So you just set your timer interrupt to run fast enough, and you just sample what the value is every so often of the DIO pin. And as soon as you can detect on that DIO pin a start bit has occurred, now you know that it's time to start paying attention to when you're transmitting data. So, alternatively, you can use your DIO interrupt and a timer. And you use your DIO interrupt, you let your timer just run free. In your DIO interrupt, what you do is you watch for changes in the value of the pin. So you can configure your DIO interrupt to interrupt on a low to high transition. You can interrupt on a high to low transition. You can interrupt on either a high to low or low to high. Maybe low. Okay, got it. Okay. So this using the DIO interrupt and the timer is a little bit more complicated than just sampling using the timer because you've got to watch the transitions. But the problem is if you have 7 zeros being sent as your data bit or 7 ones being sent as your data bits, and then you have a stop bit, you can't tell when the last data bit gets sent and when the stop bit starts. So all you can do is just denote what time a transition occurred. So you get an interrupt every time a transition occurs, and then you figure out what time did that transition occur. So then you have to go through and back out and say, okay, well, a transition occurred 7 bit periods ago, and now a transition's occurring. So does that indicate I got a stop bit or not? And if you do end up with a stop bit, then you can start to discern, okay, I got this data bit, this data bit, this data bit, and I've got this stop bit. And the stop bit was at the time it should have been, and the start bit was at the time it should have been. So therefore, we have communicated successfully. So in either way, what you end up doing is you have to be able to detect when a start bit occurs. So the general algorithm for the receiver on the TS7200 is as follows. First step, you wait for a start bit. So you're just periodically checking to see when that start bit occurs. After a start bit, you wait for 1 bit period because the start bit's going to happen. You're going to have you've got to wait until the start bit has been held on the line for the total time that the start bit needs to be on the line. Okay? After that 1 bit period has expired, then you read D0. That's the first data bit. And then you wait for a bit period. Then you sample D1 and you wait for a bit period. You sample D2 and you wait for a bit period and so forth. Then you sample D7, you wait for a bit period, and then you read in the stop bit. And your stop bit had darn well better be logic 1. If it's not, you've got a framing error. Okay? So you check to make sure your stop bit has been received and it is the value that you want it to be. As soon as you've validated that your stop bit did occur, you take these 8 bits that you've just received, you pack them together in an 8-bit word, and then you insert the received byte into an RX FIFO, and we'll talk about what that RX FIFO is momentarily. But this is effectively just a really high-level algorithm. Now, the devil's in the details, just like everything else in this class. But all you do is you just wait for a start bit. When the start bit occurs, you wait for a period of time, and then you grab the first data bit and wait. Grab the second data bit and wait. Grab the third data bit and wait. What does it mean to grab a data bit, and what do you do with that bit? Well, you somehow have to hold it and remember it, and you have to take advantage of the fact that while you're waiting, you don't just sit there and spin and eat CPU cycles. You've got to be doing other work in the meantime. So you've got to sample what the bit value is, and then go and do other work in the meantime, and then come back here and sample at the appropriate time, and then go back and do other work in the meantime. You may also want to sample at different intervals, effectively implementing oversampling, where when it's time to sample D1, instead of just sampling it once and then waiting 1 bit period, you sample it once, wait a third of a bit period, sample it again, wait another third, sample it again. And then you compare those 3 samples and you see if they all agree. And what that makes you a little bit more immune to noise. So you can average the samples together, and if you end up with 2 zeros and a 1, Well, you're going to say, well, it's probably a 0. If you end up with 3 zeros, you say, well, okay, I'm pretty confident it's a 0. I would not recommend sampling an even number of times, because then it gives you the opportunity to be confused. Don't give yourself an opportunity to be confused. There's already plenty of that going on. Okay. So this is just a high-level algorithm of the receiver. Transmitter is similar. Oversampling is a good thing, but can be taken to an extreme. Okay. So that's just the general gist of Lab 9. What are the basic steps involved in doing Lab 9? Okay. Step 1, you got to get Lab 8 working. Sorry, no way around that one. Both the RMS test bed and the table-based scheduling have to work for Lab 8 in order to get done with Lab 9. Step 2, implement PCP semaphores. We'll say that one's straightforward. Like everything in this class, it's relatively speaking. So I've given you the implementation of PCPP and PCPV, but there's a lot of, again, detail work. You have to make sure that your infrastructure that you've implemented is consistent with the implementation that I've given you. And I've tried to point out where it could be inconsistent, like with whether or not your running process is on the ready queue or not. So just be careful when you're using my implementation of PCPP and PCPV to make sure it's consistent with your system. Okay, so as soon as you get the PCP semaphores working and the corresponding command line commands and the extensions to the command line commands, as soon as you get all that working, then you dive in for the software UART. So the software UART consists of an implementation of an application that uses your operating system infrastructure. Okay, so we're going to have 3 processes: the RX process, a test process, and a TX process. Okay, what do these 3 processes do? Well, I bet you can guess. So the RX process is in charge of getting data. The TX process is in charge of sending data. Your test process is in charge of manipulating the received data and giving new data over to the transmit process. So how does RX get data? It periodically reads from the DIO input pin. Multiple ways of accomplishing this, as I've just outlined before. Effectively, it implements a software shift register. So if you remember what a shift register is, it's something that takes in bits and then shifts those bits in 1 bit at a time until you get to 8 bits, and then you can read out those 8 bits in parallel as an 8-bit word. Okay, so your RX is going to implement a software shift register. What does RX do with the received byte? So once the RX process has shifted in 8 data bits and arrived at getting an 8-bit word from the serial port, what does it do with that 8-bit word? It stores it in a FIFO. Again, this is a true FIFO, not a priority queue. So your RX here is going to be sampling your DIO pin, getting the data from the transmitter. Okay, and as soon as it gets an 8-bit word, it will enqueue that into a FIFO. So this FIFO is a shared data structure that's shared between the RX process and the test process. And this is just a FIFO. You ever implemented a FIFO before? Y'all ever seen a FIFO? A couple times, once or twice. Yeah. Told you in the beginning that the FIFO is important. So anyway, here's your Lab 0 again. That guy's just a useful data structure that keeps on bearing his head all over the place. So FIFO is just a software data structure that is shared between 2 processes. Well, again, I've said that word shared a bunch of times, and that's important because you've got 2 processes sharing a structure. So if you have 2 processes that are accessing a shared data structure, you've got to make sure that when this one accesses the shared data structure, it doesn't mess up that one's access of the shared data structure. So we have to protect this shared data structure as a resource by grabbing semaphores. So how do you protect a shared data structure? Well, that's why we need to have our PCP semaphores implemented on phase 2 in order to get, during phase 1, in order to get phase 2 working. Okay. So just so you're aware, if you are really stuck and can't get your PCP semaphores to work, you can cut your losses by using strong semaphores to protect your shared data structures on phase 2 if that allows you to make more progress. You know, I'm going to I won't double ding you. I'm going to ding you for not having PCP semaphores working, but I won't ding you again because you're not using PCP semaphores, so long as you acknowledge in your write-up the fact that you should be using PCP semaphores, but your PCP semaphores are not working. So you're going to resort to strong semaphores. So you should be using PCP here. If your PCPs don't work, then you're going to use strong semaphores. Okay. The other thing to note is that you want to make sure you have small critical sections. By small, I mean as few instructions as possible. You want to make sure that when you grab a PCP semaphore that you're only doing the smallest amount possible to access the shared data structure and then give up the PCP semaphore. The reason why is because you don't want to mess up the interaction between the processes and their priorities. You want to make sure that the priorities of the processes govern their execution, not the ownership of the PCP semaphores. So keep your critical sections as small as possible. Okay. For your transmit side, your test process is going to take a piece of data that was received, it's going to monkey around with it, and then it's going to ship it back off to the transmitter. So there's another shared FIFO between your test process and your transmit process. And your test process here is going to insert data into that FIFO. The transmit will remove data from that FIFO. The transmit process will send it on out the other side of the serial port using your software emulation of RS-232. And so again, another shared data structure that must be protected. So test process, the implementation of test process is going to look something like this. Void test process, it takes an unsigned int. Again, this is just the similar prototype for a process that you guys have seen before. We declare a char A, and then we have this forever loop in here. A equals get next RX char. Then we say A or equals get mask char, and then send next char to TX. So this function, get next RX char, is what interacts with the receive side FIFO and grabs the byte that was most recently received. The next thing that we do is we OR that received byte with a mask. Where do the masks come from? The mask is an 8-bit integer that the user specifies via the command line. You can have a default value, but the user should be able to alter what mask value you're using by sending down a new value of it using a command on your command UI. Okay, so that'll be another command that you're going to add to your user interface. So you've got to get this mask character from the memory location that's being updated by the UI. You OR A with that, and that'll give you a slightly, hopefully, altered version of what what the transmitter transmitted and what the TS7200 received. So you get that byte, you change it just a little bit, and then you send it back to the transmitter with a send next char to TX. So what that'll do is it'll enqueue this A value that we've just updated, and it'll send that to the TX process, and the TX process will send it on out the DIO port to whoever is listening on the TX side. Okay, what does get next RX char look like? So it's going to look something along this lines, where you're going to have a semaphore that protects. So again, your get next RX char is something that runs as part of test process, but interacts with the RX process by grabbing data on the FIFO that those two share. So there's a semaphore that will protect that FIFO on the RX side. We'll grab the FIFO with a PCPP, then we'll remove an entry from the RX FIFO, put that into the variable N. We'll give up that semaphore that protects the RX FIFO, and then we'll check to see whether or not there was a value there. If there was no value, if there was a value there, we return the value in. Otherwise, we go back up and we check again. So all that we're doing is effectively polling that RX FIFO. There are different ways of doing this. You don't necessarily have to poll. If you want to get around polling, that's fine. Go and do something else, but make sure you do protect your critical sections. Okay, so how do you implement the FIFO? CLAB 0. How do you implement send next char to TX? It's similar to the receive, except for you're using the TX FIFO, and then you're inserting instead of removing. Why am I inserting? Well, because the TX side of the FIFO, this is the value that the test process takes and manipulates, and now you're going to send it on to the transmitter. So we're going to insert it into the FIFO that the TX process will be polling to pull data out of, so that it can send it on up out the RS-232 emulated lines. Okay? So the other thing you should do inside when you're inserting into the TX FIFO, you can check to see if your FIFO is full. We didn't really have a metric of full when we were talking about Lab 0 because we had these FIFOs that could grow indefinitely. One thing that I did want to make you aware of, this applies both to Lab 8 and Lab 9, there are times and situations that we haven't been able to really put our finger down where calling malloc messes things up. And it's not that malloc is getting called inside an interrupt service routine or it's getting called inside a process or getting called anywhere else. Sometimes and in some circumstances, calling malloc messes things up. I don't know why. So I can tell on many circumstances the reason why calling malloc messes things up is because the students who are calling the malloc are not using their pointers correctly and are dereferencing garbage pointers. That happens a lot. But I have also seen code where I can't find any dereferencing of a garbage pointer, and yet the code is still weird. And so I would recommend that you not call malloc anywhere in your code. That would include your FIFO implementation. That would include any stacks that you're creating. That would include any tables that you're creating. Don't call FIFO. Don't call malloc. Okay? So then if you're going to need to allocate stuff at runtime, how do you not call malloc but yet still do dynamic memory allocation? You have to do some type of management of your own memory pool. So if you need to allocate a new semaphore, you just pre-declare at the beginning of your semaphore file a pool of maybe 20 semaphores, and you keep a global static integer counter that says, I'm allocating number 1, I'm allocating number 2, I'm allocating number 3, and you just keep track of which semaphores you've given to where so that you don't reallocate a previously allocated semaphore. But you just declare them statically as an array. Similarly, you can declare similar stuff for this FIFO. This is going to be a little bit harder to do because you're going to have to scrap most of your implementation of your FIFO and just use a simple, it depends on how you want to go about it. I mean, you can just re-implement it as an array and just shift data items around in your array of the FIFO elements, or alternatively, you can declare statically a pool of FIFO node structures and keep pointers into the FIFO node structures and allocate them and deallocate them. The other thing that you can do is do an analysis of how deep you want your FIFOs to be and just statically declare FIFOs of that depth, and then manage if you're removing from an empty FIFO or if you're inserting into a full FIFO, and vice versa. So don't malloc. That's the bottom line. All right. Next question, how do I implement get mask char? So get mask char is, this accesses a shared variable. That variable can be altered by the UI. It's shared by test process, and it's also shared by the command interpreter. Why is it shared by the command interpreter process? Because the command interpreter process is responsible for interacting with the user. The user says, I want to change the mask, and sends down a mask value of 0xAA instead of 0x55, then the command interpreter process has to update the mask variable. So in order to be able to do this, we have to make sure that the mask variable that we're accessing, that is a shared variable. So every time we access it, we have to grab a PCP semaphore that protects it. So we do PCP P on a semaphore that protects the mask. We get a local copy. This char M kind of looks like charm, but it's just declaring a char called M. We set M equal to a copy of mask, and then we do PCPV on the semaphore, and then we return M. So we just use this to acquire a local value of the mask, and then we return that local value. So the UI, when it's going to update the mask, it would do a PCPP on the semaphore protecting mask, and then it would write the value that it's going to write to it, and then it would do a PCPV. Again, the other thing to watch out for is when the command interpreter grabs a PCP semaphore that it shares with test process, that means its priority, its dynamic priority, is going to get elevated to the point of test process. And when you have that dynamic priority elevation, you've got to make sure that the UI doesn't sit at that level for a long time, because otherwise that could mess up the acquisition of the bits inside your receiving process and could mess up your UI. So we don't want to have the command interpreter get elevated to a higher priority for very long. We want to have that happen as little as possible. But it's necessary in order to protect the critical section. Okay. How do I read the input pin? So labs 3 and 4, you triggered the RPM interrupt based on a level change on the DIO pin. There are 2 approaches to reading the pin in this lab, and I mentioned them briefly before. You can, number 1, use the RPM interrupt to note when the pin level changes. So you can set up the RPM interrupt to transition on low to high and high to low. And so you can just note the times at which you have a low to high transition and the time at which you have a high to low transition. So you just have your timer running all the time just as a way of telling time. And then inside your RPM interrupt, you're noting the times of the changes. And then as soon as you've gotten a big enough sample, then you can go back and look at where was my start time, where are my data bits, where's my stop time. Okay, so the other approach is just periodically sampling the pin based on the timer interrupt. So you run your timer interrupt faster. So you run your timer interrupt fast enough so that you can sample often enough so that you can detect when the stop bit is, when the start bit is, and when the data bits are. So in order to do this, you would explicitly read the DIO pin. In order to do that, you would set GPIO pin 0 to input under the assumption you're using GPIO pin 0 as your input pin. Do not set the interrupt source for the GPIO, and do not set up an IRQ for GPIO. This is just for number 2 here if you're doing periodic sampling. If you're doing periodic sampling, you don't want to interrupt on the DIO. You only want to interrupt on the time, and then your timer interrupt will explicitly read the DIO. Okay? So back in those labs, Lab 3 and Lab 4, we used the following code to write to GPIO1. So we had this macro that said send DIO high, had this do while loop that ends up getting compiled out. We referenced GPIO PBDR and ORed that with DIO 1 bit. And then we would do, we had this for send DIO high, and we also had send DIO low. When we do send DIO low, instead of ORing bit 1 with a 1, we would AND it with a 0 to make sure that it's a 0. Okay, so you set the bit to send a high, you clear the bit to send a low. GPIO PBDR stands for General Purpose I/O Port B Data Register. So this is the name that the TS7200 guys, I'll make sure it's the TS7200 guys and not the Cirrus Logic guys. So I can't remember who named it, but they named it. I didn't name it. So anyway, the GPIO PBDR, this is a data register consisting of 8 bits, and this is how you access all the 8 DIO pins on the port B. Okay, so there's a port A, there's a port B, and there's a port C. I think port C has 2 DIO pins available, and port A, if I remember correctly, that's where the LCD is, but I could be wrong on that one. Anyway, GPIO PBDR, this is how you access those pins in that header that we're going to. You can access more than one pin. So for output pins, you write a 0 to the appropriate bit to get 0 volts on the output pin. You write a 1 to the appropriate pin in the GPIO PBDR to get a 3.3 volt to appear on that, under the assumption that you've configured the corresponding pin to be an output. Okay? So you have to configure the pin, and then you can write a 1 to it to get a 3.3 volts on that pin. You can write a 0 to it to get a 0 volts on the pin. For reading, you just read the port register and mask off the appropriate bit that you're after. So this is kind of silly, or not silly, but it's kind of counterintuitive, but you read from GPIO PBDR in order to do a receive. You write to it in order to write. Okay? Now, why it's kind of counterintuitive is because if I write to bit 1 of the GPIO PBDR, I'm sending or asserting a 1. I use the same address, the memory mapped address, in order to read from the bits of the GPIO PBDR. The only ones that make sense when you're reading them are the ones that are configured as input pins. Okay? So if I say val equals star GPIO PBDR, and, again, there's a bitwise AND, DIO 0 bit. What that'll do, this is a mask, GPIO 0 bit, this is a mask that masks off all the bits in that value that I pull from the hardware register, the port B. It masks off all the bits except for the least significant bit, bit 0. So val will either end up being an integer 0 or an integer 1 because of this bitwise ANDing. So GPIO PBDR is a pointer. It's a pointer to an absolute address. That absolute address is in the memory space of the TS7200. That address does not map onto RAM. It maps onto an actual hardware register. That hardware register is tied to traces on it's tied to pins on the Cirrus Logic chip that are tied to traces on the board that go over to the header that's on the board that you put your little wires onto. Okay? So this looks like a memory read, but it's not actually accessing memory. This is what you call memory mapped I/O. So you've got a memory location that doesn't correspond to RAM. It actually corresponds to a port, and you can assert pin values on that port. And you can also read pin values on that port. Yeah, Mitch.
So if we weren't using DIO 0, we need to do a shift as well.
So if you weren't doing DIO 0, if you're just trying to see whether or not the pin's asserted or not, you wouldn't need to do a shift, because what you'd do is if you were using like DIO 3, you would have a mask over here that says read in the port B data register, and then mask off all the bits except for bit 3, and then you just see whether or not that resulting value is a 0 or not. If it's a 0, all the bits will be 0. If it's not 0, then only bit 3 will be asserted. You would ordinarily shift that down to be bit 1, but it doesn't matter. If it's non-zero, then you know that there is one bit that's asserted, and the only bit you're allowing to be asserted is the one that you're masking. Okay, now that we know a little bit about what this port is, again, memory mapped register, you can write to it, you can read from it. You have to configure each individual bit to be the sense that you want it to be, whether input or output. And you use those functions that I've given you in the GPIO.C and GPIO.H to set the directionality of the pins. But given those resources, and given the fact that we know where the GPIO PBDR is in memory, there's nothing saying you can't use bit 3 and bit 7 for your transmitter and your receiver for input and output. You can choose which bit you use on that header. Okay? Which pin on the header is which bit in the GPIO PBDR. That correspondence I gave out when I talked about Phase 2 in Lab 3, and I told you which pins are what. So just be careful that you're testing which pins are which pins. Okay. A note on time. If you're using 400 baud, that means you're transmitting 1 bit every 2.5 milliseconds. 400 baud, as serial ports go, is pretty low. Anybody know what the baud rate that we're using for transmitting our printfs back and forth? Yeah, like 145. It's more than 100,000. So it's very fast with regard to this. So this is 400. We're using more than 100,000. Okay. So if you have a process, so you're transmitting a bit every 2.5 milliseconds. If you run a process that has a period of 2.5 milliseconds, that means you've got to swap this process in every 2.5 milliseconds. Given the context switch overhead and the scheduler overhead, you're not going to get much else done. There won't be much more slack in your schedule. So this is a very, very fast period with regard to the capability of our board and the context switch overhead that we have. So because of the fact that you might be able to make this work if you're running a process that all it does is wake up, sample a bit, go back to sleep. You might be able to make this work, but you're not going to have much slack time in your schedule in order to run your UI. So what I would advise you to do is consider the execution of bit level operations within a timer interrupt or within another interrupt if you're going to use the RPM, the GPIO interrupt, and then do byte level operations within a process. So what this would mean is your timer interrupt fires fast enough so that you can just sample the bit and then get out of Dodge with your timer interrupt. Further, there's nothing saying you can't have 2 different timer interrupts. One going off of timer 1, another one going off of timer 2. you want to go in that direction, I can even help you set up the second timer interrupt. But the code that I have set up should be able to do 2 timer interrupts. You don't have to use 2 timer interrupts. This is only one if you want to slickify your implementation. Well, there are lots of people who like to slickify. Most others like to simplify. There's nothing like simplification to make something work. You don't have to use 2. You can get away with just 1. Okay, I'm going to hold off there, and we'll continue this next time. We'll finish off talking about Lab 9. Answer any questions you guys may have about Lab 8 or Lab 9. We're almost done. Hang in there, we're almost done. Yeah.